Cool. All right. For this one, we're going to talk about something called quantum numbers. This is directly related to what we've been talking about in terms of quantum mechanics. Okay. Um, yeah, my brain just collapsed in on itself again. I'm sorry. Um, yeah. So what we're getting at here is this idea of quantum numbers. Um, remember we talked about Schrodinger's equation, and we said that the psi here is the wave function, and the wave function defines the orbital. Really, what happens is that this defines something called the quantum numbers. Okay. Quantum mechanics uses 3 quantum numbers. We're going to stick with those today. Um, and the quantum numbers define and describe what the orbitals look like. Okay, and we'll see that eventually as we talk about stuff. Okay, so for reference, right, Bohr used a quantum number, although he didn't think of it as a quantum number because that wasn't a thing when he did it. But Bohr's integer value of n for the energy level was in fact a quantum number. So Bohr had one quantum number. Quantum mechanics has 3 quantum numbers. All right, let's get into this. All right, and for some reason we can get bogged down into this. It's not as complicated as you think it is or are worried that it's going to be. Okay. We're going to go through this one at a time. I just want us to know what the rules are for these um, and what they mean in terms of the orbital. Okay. So the principal quantum number, this relates back to Bohr's value of n. So we still call this n. Okay. It defines the size of an orbital and the energy of the orbital, and it defines the energy level or the shell. Sometimes you hear about electron shells; they kind of mean the same idea. The value of n could be any positive integer, so this could be anything from 1 to infinity. But all the elements we're dealing with right now only go up to 7, so uh, we're fine with that. This is directly related to Bohr's n. What we can think about this is the larger, right, a larger value of n means you're a physically larger spelling, a larger orbital, which means those electrons can get farther away from the nucleus. It also means that you have a higher energy. These two things always go together. Okay, a larger orbital and a higher energy always go together. The farther away from the nucleus you are, the higher energy the electrons are, right? Because they're farther away from that stabilizing positive charge. Okay. What's next? Okay. Angular momentum quantum number. This is L. L is probably what we're going to think of as one of the more important ones. L defines the shape of an orbital and what we call the subshell. Okay. So this is like nesting layers of stuff. So N defines generally the value of the energy and the shell. Okay. Inside that N level are sublevels that are defined by the value of L. Okay. Um, the value of L depends on the value of N. It has a max value of N minus 1. Okay. And we're going to work through that and define what it means. So essentially, L can be any integer from 0, 1, 2, 3, yada, 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 with the max value of N minus 1. So L depends on N. Okay. If you ever need it for anything, this is also known as the azimuthal quantum number, which no one uses that anymore, I don't think, but it's a fun word to say, azimuthal. Okay, L depends on N. So let me see what the next slide is so I don't, yeah, okay, I need to come back. Yeah, we're good. Okay, L depends on N. So if N equals 1, then L can only be 0. Okay, because N minus 1 is the max. You can't have N equals 1 and L equals 1. If N equals 2, then L can be 0 or L can be 1. So there's 2. So what this tells us is This is one subshell. This is two subshells because there's two possible values. There's a 0 subshell and a 1 subshell. Okay, you take this further, n equals 3. So this would be L has to be 0, 1, or 2. And then there's 3 subshells here. Okay, you see what we're getting at here? We're just nesting layers together. Okay, and you can take this, out as far as you want to go. If you want to say n equals 10, okay, well, then for n equals 10, L could be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Okay. Notice here, though, that the number of sublevels is equal to the value of n, right? Because if L equals 0, that's one value, that's one subshell, the n equals 1, right? And that's true for all of our levels. Okay. Now, as far as subshells go, we can denote subshells using something called subshell notation. And all that means is we are assigning a letter value to L. Okay, so we can translate them through. L equals 0 means S, L equals 1 means P, L equals 2 means D, L equals 3 means F. If we ever have 4, then that's going to be G, 5 is H, 6 would be I, and so on and so on. Okay. I'll give you a spoiler for later. We don't have anything bigger than F right now. If you're curious why these letters are like this, these are named after what the data look like when they're looking at these things. And so they call these sharp, principal, diffuse, and fundamental, which is where SPDF comes from. Beyond F, they just go alphabetical order. So G, H, I, J, K, blah, blah, blah. Okay. If we're going to do subshell notation, the subshell notation tells us both the value of n and the value of L. It's going to use the number value for n and the letter value for L. So for example, we said if n equals 1, then L has to be 0. Okay, so our subshell notation here is going to be 1s because L equals 0 is s. This is also how we're going to refer to where electrons are in the atoms, and so it's important that we get this down. Okay, so if n equals 4 and L equals 2, right? N is 4, so this is a 4. 2 means D, so this is a 4D subshell, or we could say it's a 4D orbital, it's a 4D subshell. We can all kind of go through that as we do it. We should also be able to do this the other way around, right? If I tell you we have a 5F orbital, we should be able to come up and say, well, that means that N equals 5 and L equals 3. Okay. We also need to be able to determine that if things exist or don't exist. So if I ask you about a 1p subshell, does that exist? Well, let's define what 1p means. 1p means n equals 1 and L equals 1. Can L equal 1 if n equals 1? No. So this does not exist. Okay. So we got to be able to figure those kind of things out as we go. Our third quantum number is known as the magnetic quantum number. Okay. And this is called m sub L. Okay. And this tells us the orientation in three-dimensional space. Okay. How is that orbital oriented on the axes to look in 3 dimensions? Okay. This depends on the value of L. So, and it ranges in values from minus L to 0 to plus L. Okay, so what does that mean? And a lot of times you'll see this as 0 to plus or minus L, which is the same kind of idea. Okay, so let me go back. We bumped it. Okay, so if L equals 1, let's start with L equals 0 because L can equal 0. L equals 0, then M sub L has to be 0. Okay. You can think of it this way, whatever 0 looks like, there's only one way to orient it in three-dimensional space. So there's one orbital there. Okay. If L equals 1, then M sub L could be -1, it could be 0, it could be +1. Now this tells us some stuff here. There are 3 different ways to orient whatever an L equals 1 orbital looks like, and we'll see those later. Okay. Because there's 3 ways to do it, there are 3 orbitals in the subshell. So the number of orbitals in a subshell is equal to the number of values of M sub L. Okay. So here we have 3 orbitals in that subshell. Okay. Now, if L equals 2, then that would mean that M sub L is -2, -1, 0, +1, or +2. Okay. So this means that there's 5 orbitals there. Notice a pattern here too, that the number of orbitals in a subshell is equal to 2 times L plus 1, right? You have the positive numbers, you have the negative numbers, and you have 0. So that's 2 times L plus 1. So if you wanted to look at it and say, okay, if L equals 9, you could write out all the numbers from -9 to +9. Or you could say, well, 2 times 9 is 18 plus 1 more is 19. So there should be 19 orbitals here. Okay. Because of that +1, this number is also always odd. Okay. So remember, we can think through that. So we can also relate this back to subshells, right? So if we had a 3, that doesn't exist, a 4F subshell, we can figure out how many orbitals are there. We can do it both ways. F means L equals 3. L equals 3 means there are 7 orbitals. They're going to have M sub L equal to -3, -2, -1, 0, +1, and +2. Okay. Does that make sense? The number of orbitals in a subshell is one of the more confusing things, but it depends on the value of L, right? And the number of the number of possible values of M sub L, which is why it depends on L. Okay. So you can always think of it this way: S is 1, P is 3, D is 5, F is 7. And if we had them, G would be 9. None of the elements that we currently know have orbitals and have electrons and G orbitals. So we're not going to stress about it too terribly much. Okay. Here's a nice little summary we have. I caution against like brute force memorizing all of the quantum numbers. Just learn what the patterns are so that it's easier to work through that. And like I said, there's layers as we do this, right? This would be n equals 1, n equals 2, 3, 4, and so on. We also want to pay attention to that the number of subshells in a level is equal to the value of n. Number of orbitals in a subshell is 2L plus 1. What about the number of orbitals in a level equals n squared? Let's think through this. N equals 1, 1 squared is 1. There's 1 orbital there. N equals 2, 2 squared is 4. 1, 2, 3, 4. There's 4 orbitals there, and so on and so on. N equals 3, 3 squared is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 orbitals there. So that does work. And remember about recognizing subshells that do not exist. Okay. The other thing we need to worry about here is, can we determine if a set of quantum numbers is allowed or forbidden? Okay. Allowed just means it follows the rules of the quantum numbers, and forbidden means it does not. Okay. So let's look through this. This first one here, okay, if n equals 5, then L has to be less than 5. That's good. And if L equals 2, then M sub L has to be between -2 and +2, and this is -3. So this does not work. This one is forbidden. Okay, we can go through all of this. N equals 0, that can't work because 1 is the first one. So that's also forbidden. Okay, if N equals 2, that's okay. Then if N equals 2, then L has a max value of N minus 1. So this has 1 max. So this can't be true. Okay, because this can't be 2. Also forbidden. On the last one here, if N equals 3, 3 is reasonable. 3 means L has to be max of n minus 1, that's 2, so that's okay. And if it's 2 here, this has to be between -2 and +2, and that is also true. So this one is allowed, and the rest of them are all forbidden. Okay, so we got to be able to look through those as we do it. All right, the last thing I want to get at is the fourth quantum number. And I know I said there were 3 before. The first 3 quantum numbers deal with the Schrodinger equation and defining the orbital. Okay, the fourth quantum number isn't related to Schrodinger's equation at all. Okay, and it relates to electron spin. So let's talk about electron spin. Okay, this was figured out by Stern and Gerlach. They are shown here. This is a great experiment. So what they did was they had silver atoms they fired silver atoms through a magnetic field. Okay, what they saw was that instead of going straight through or all of them going in one direction, they split and half of them went up and half of them went down. Oh, excuse me. Okay, so what they realized was that half of them are attracted to one side of the magnetic field and half of them are attracted to the other side of the magnetic field. So somehow these electrons have magnetic fields in them. Okay, these atoms have magnetic fields in them, and we can do that. Okay, so what they figured was, and if you take an electrical charge and you spin it, you generate a magnetic field. So if you have an electron spinning in one direction, you get one kind of magnetic field. If you have the electron spinning in the other direction, you get the other kind of magnetic field. Okay, and so depending on which direction it spins is which kind of magnetic field you get. Okay, and I love this little bit of history, right? And I love this picture of Otto Stern smoking a cigar in lab because that just kind of dates everything as we do it. But if he wasn't smoking a cigar in lab, we might not know about this. This is their actual data here. They're looking at silver atoms on a piece of, actually at this point, it was a piece of paper or some sort of screen, some physical media here. And actually what happened was the smoke and the ash from the cigar reacted with the silver and made the silver become visible. And that's how they saw it, was that the pattern looked weird and it was the smoking let it off, which is interesting. Anyway, so this defined for us, maybe, the new quantum number m sub s. Okay, this tells us which direction the electron is spinning, so it tells us whether or not it is which kind of magnetic field it is. Okay, and so they coined these as spin up or spin down. Okay, so up was represented with an arrow up and down was represented with an arrow down. Okay, they call this plus a half and minus a half. Okay, and if you have electrons of opposite spin, you have one up and one down together and they cancel the spins out. Okay, so we call this paired. If you have one up and one down, the spins cancel. And we'll come back to that thought later on. Okay, but the plus 1/2 minus 1/2 is m sub s. So there's only 2 possible values. And this also has consequences that we will get to when we start thinking about where in the atom electrons actually are. Okay, I'll catch you next time.